Welcome to the lecture on heat flow in welding. So, we discussed in the last class about the classification of welding processes. Now, most of the welding processes what we see, majority of them are the fusion welding processes. And as we know that in fusion welding processes, you have the application of heat to a certain region, and then that region is melted, further it is solidified. So, this way you have the application of heat, there is heat source, then there will be transfer of heat from that region, that is weld metal zone, to the surrounding areas. So, this way the heat application and further its dissipation basically affects the properties of the material. The microstructure or structure of the material changes because of that. So, in this lecture we are going to discuss about the heat flow in welding, how the heat is flowing, in what mechanism the heat is generated, not in a very depth manner we are going to discuss about it, but we just have to have some understanding that how the temperature field is generated, how there will be isotherms generated, what will be the concept of these, how that is useful for further in future if you want to predict the microstructure, then how these concepts will be used in finding those details. So, as we discussed that all the fusion welding processes, they involve heat flow during the welding. So, fusion welding means you have a zone, fusion zone, or you have basically a zone which is basically fused, which is melted, and then that melting is normally done by a type of heat source. So, you have a source which apply the heat, and that goes, and then when adequate heat is applied, that basically melts the parent metal, and if required the filler metal or so. So, that way you have the involvement of heat flow during the welding. Now, because of that you have different types of microstructures which are obtained depending upon the heating and cooling cycle. So, what happens that when you have a sheet or when you have two plates which are joined, so first of all they are heated, and then while heating the temperature is increased. So, suppose you are welding two sheets, like you have these two sheets, and if you want to have the joint here. So, what you do is in this joint you are applying the heat. Now, because of this application of heat, this zone's temperature goes on increasing. So, this here the temperature is increased, and then this temperature which is increasing, because these are the metals in most of the cases and it has some certain conductivity. So, this heat will traverse to these directions. So, the heat which is applied to this place, because of that there will be basically expansion, and there will be associated phenomena because of that heat. Then further that heat, once the heat is accumulated here, this heat tries to spread in the transverse directions or in these directions like this, okay. And then once they traverse towards this direction, they will increase the temperature of these zones slowly. These zones temperature will be increased. So, at the very far end the temperature may be the room temperature, but here the temperature will be higher, then higher, and then higher. So, this way you have heating, then further after some time they will again start cooling. because this starts dissipating the heat slowly and then further. So, it will be heated and again slowly because it is in the environment. So, again it is dissipating the heat to surroundings. So, slowly again its temperature will come down. So, you will have a cycle, you have you can see that the material passes through a heating and a cooling cycle. Now, because of this heating and cooling cycle, the different kinds of microstructures are obtained depending upon what kind of heating and cooling cycle is there, how quickly the heat is increased, how quickly heat is decreased, temperature is decreased, basically how quickly heat is added and temperature is increased, or how quickly the temperature is decreased. So, depending upon that, you will have the different types of microstructures which are obtained. So, this all is because of the heat flow or the insertion of heat into that particular zone. Now, because of this, the other effect is that there may be formation of residual stresses, distortion, physical and chemical changes. So, because that will lead to here what happens that because of these differential thermal cooling or heating, there will be the formation of residual stresses. Now, these residual stresses may lead to distortion. So, there may be the distortion means the body becomes out of shape. Then there may be physical change or there may be chemical changes like chemical inhomogeneity may be generated. So, this is all because of the modified structure also. You will have these are the end effects of this heat flow. So, now coming to the thermal distribution in welding. So, what we see that most of the welding processes are, so about 90% of the welding process which we talk about 90% is based on the arc welding process. So, among the all the fusion welding processes, you have about 90% is from the arc welding, because arc welding is simple and it is very effective. So, normally we use the arc welding process. So, now what we see is that the heat flow into the body is primarily by conduction. So, as we see that when we are having the heat flow, now that goes into the body mainly by the conduction, and partly a very small percentage is by convection. So, the by radiation also it goes into the atmosphere and even by convections, but that percentage is quite small. Now, if you look at the welding process, what is there? So, you have two plates, you are welding in a particular direction with certain velocity. So, you will have a direction of welding. So, in which direction you are moving, so you will have a direction of welding. Now, when we try to analyze this welding process, then in that case what we see is you can assume it as a conduction problem with a point heated source and that is moving. So, what we see is that you have two plates. So, you have, suppose this is the plate and you are basically doing the welding along this direction, suppose. So, this is your welding direction. So, in that case if you look at, it is nothing but this is a problem of conduction, but then you have a heat source here. So, you have a heat, this is a heat source and this heat source is moving. So, basically you can assume this is primarily by conduction, heat flow of body flow into body of welding is by conduction, and then heat input is by a moving source. So, that is what that way we define this welding process. Then again this is assumed a condition of quasi stationary state. So, what does that mean? That means that the observer at the arc what he sees, that he sees a fixed temperature field all around the arc at all times. So, basically dou T by dou T, so that will basically becomes 0. So, that's a case of quasi stationary state. So, basically if you look at any point, what he sees is that all the point distant to it, now these points are at a fixed temperature. So, what he sees is that there is a fixed temperature field all around arc at all the times. So, that is a case of quasi stationary states, and this way you will have the formation of isotherms. So, isotherms are nothing but you have the lines of constant temperature. So, that is known as isotherm. So, you can draw these isotherms for the process, and you may have these isotherms which will represent the different temperature remain at a fixed distance with respect to the heat source. So, what we see is normally when we talk about the case of such quasi stationary state, and when we talk about the isotherms, you can see that suppose if you are looking here, you will see that your temperature will be here, it will be like this, then it will be coming like this way, it will be going and that way. Okay. Now, similarly, if after some time it goes here, so in that case you will have a temperature line here, then you will have this type of. So, this way these are known as the temperature isotherms. So, this is nothing but if you look at this point where the heat source is there the weld pool is there at that particular time. Now, at this point this temperature is highest here. So, this temperature if you look at this is point 1, 2, 3 or 4. Now, if this is T1, T2, T3 and T4. So, like this is T1, this is T2, this is T3, this is T4. In that case T1 is greater than T2, greater than T3 and greater than T4. So, this way these isotherms are drawn, which basically talk about the temperature, different temperatures which are at a fixed distance with respect to the heat source. Now, we will talk about the metallurgical effects. Now, before that let us see how these conditions come. Now, the thing is that if you talk about this thermal distribution in welding, where we talked about the different kinds of isotherms. Now, how these isotherms are drawn, basically as we discussed that basically it is the solution of a problem of conduction, and this conduction is having a source also, that is heat source. And if you talk about the law of conduction, then there is a very renowned equation of conduction, that is Fourier law of conduction. So, Fourier law of conduction can be applied in this case also. Now, in that, as we know that Q will be minus of K into A into dou T by dou X. So, that is your amount of heat, that is Q in case of conduction. Now, if you talk about the 3-dimensional Fourier law, so Fourier equation of 3-dimensional heat conduction in solids, what we get is that dou square T by dou X square plus dou square T by dou Y square plus dou square T by dou Z square, it will be nothing but 1 by alpha dt by dt. So, that is what the Fourier equation of heat conduction is. So, then where alpha is nothing but K by rho Cp. So, that is what the Fourier's law of heat conduction is, but in this case you have a moving source. So, if you take that example where you have a moving source. In that case, in the x direction, if suppose it is moving in the x direction, the x coordinate has to be replaced with certain other parameter. So, you will have a welding velocity. Based on that, you will define another parameter, that is and basically what you see is that if at any point this is the x, then if it is moving with speed v, then the distance will be x minus in after time t, it will be x minus v times t. So, x distance will decrease by that. So, that way another parameter will be defined. So, if you first of all what we see is that you can use initially the 3-dimensional Fourier's law of conduction, that is dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square equal to 1 by alpha and dt by dt. So, that is what the Fourier's law of 3-dimensional heat conduction is. Now, the thing is that if you have a plate, if you have such plate, so in that, and if your weld bead is like this, so in that case suppose you are going to at some distance x, and if you have any point P. Now, the thing is that your source is moving with velocity v. Okay. So, once it is moving with velocity v, in that case this x. So, if this is the direction x, this is the direction y, and your thickness. So, it has some thickness. Okay. So, it has certain thickness like that. Now, the thing is that this is the thickness. So, in this thickness it moves. Now, the thing is that once it is moving in that particular x direction, so what you do is you have a new coordinate system with respect to the tip of the electrode. So, that is moving in x direction. So, what we do is we define, and it is moving with velocity. Velocity is v in this direction. So, we define zeta as x minus v t. So, that is basically because the source is basically moving in the x direction with velocity v. Now, in that case the equation for quasi stationary state of welding comes in terms of zeta. In place of x it comes there. So, it will be dou square t by dou zeta square plus again dou square t by dou y square plus dou square t by dou z square, and that becomes equal to minus of 2 lambda v into dou t by dou zeta plus 2 lambda into dou t by delta t. So, that way it becomes that. So, that will be dou square t by dou zeta square plus dou square t by dou y square plus dou square t by dou z square. So, this will be on the left hand side. On the right hand side again you will have another terms coming that will be function of alpha as well as v. So, first term will be minus 2 lambda v, and that will be dou t by dou zeta. So, minus of 2 lambda v and dou t by dou zeta, and second term will be the transient term dt by dt, and for that you will have 2 plus 2 lambda and dou t by dou t. So, that is basically a transient term. That basically gets cancelled because of the quasi stationary condition. This is cancelled because of the quasi stationary condition where dou t by dou t is taken as 0. Now, in this case the lambda is 1 by 2 alpha. So, this equation is solved and you can get the isotherms, because here you have depending upon the V. So, this V is also coming into picture, you have alpha that is coming here. So, it is all because of the definement of this another parameter, that is zeta, that is x minus Vt, and this way you can have the formation of these temperature contours or isotherms, and these isotherms are further used for the prediction of microstructures. Now, the thing is that this can further be solved with the boundary conditions, and you get another equation. So, that is T equal to T naught plus again e raised to the power minus lambda, then V, then zeta, and then again phi of zeta yz, like that. So, that way what we mean to say that you will have this equation which needs to be solved. So, you must have an understanding of how these equations are coming. So, you know that this you directly get it, this is this you are getting by direct normal analysis in a pure heat transfer problem, and then you get this by using or by replacing this x with zeta, that is x minus Vt, and then this way you try to get the solution of these heat flow equations. Now, the thing is that based on that, when you try to draw the isotherms, then you get this particular type of isotherms, and these isotherms talk about the kind of temperature history in a particular type of welding process, and then based on that you can predict the properties or microstructure in the welded specimen or so. Now, we will talk about the metallurgical effects of the welding process. The thing is that temperature at any given point during welding can be determined using equations that we already discussed. So, we discussed that you can find what will be the temperature at different points, and then therefrom the thermal histories can be drawn. Now, these thermal histories are used to draw the isotherms of different temperatures, keeping the weld pool as the innermost isotherm representing solidus temperature. So, here once you draw these isotherms, this temperature is nothing but it will be near the solidus temperature, and then all these temperatures are decreasing from there. So, depending upon the shape of the isotherm may be of this shape, or the isotherm may be of this shape. Now, both these shapes have a different meaning. So, in this case this temperature is on this periphery, you have same temperature, whereas in a very small periphery you have this temperature. Now, depending upon the different types of welding conditions, whether you are going at a fast rate or a slow rate, you will have the different types of welding isotherms, temperature isotherms. So, the innermost isotherm will be representing the solidus temperature, and then the outermost isotherms will be the temperatures at lower values. Now, so from these isotherms you can have the cooling rate determination. So, once you know these isotherms at different points, then cooling rate can be found, and once you know the cooling rate, then from there you can predict the microstructure and mechanical properties, because you know that you have different types of curves. You know that when there is transformation, then depending upon the cooling rate you will have the transformation products, like you have TTT or CCT diagram which are there available. So, how is the isotherm looking at, how you see the isotherms, and depending on the spacing at different points or so, you can predict the microstructure of and the mechanical properties in such cases. So, this way you can say that here the property will be or the phases will be like coarse perlite or fine perlite or benite or martensite or so. So, depending upon that you can predict that. Now, coming to the efficiency of heat sources. So, what is the efficiency of heat source? Now, the thing is that we use the heat source to basically transfer the energy to the workpiece. So, you have certain energy which is of the heat source, and how much energy has been used by the have been transferred to the workpiece. So, the energy which is transferred to the workpiece, that divided by energy generated by the heat source, that basically is known as the efficiency of heat source. So, if the efficiency of the heat source is known, in that case the energy transferred to the workpiece can be found. Now, the thing is that the efficiency is denoted by the formula, that is eta. So, this eta will be basically energy transferred to the workpiece and divided by energy generated by the heat source. So, that is energy transferred to the workpiece, and so you can write energy transferred to workpiece. So, if it is Q, and then you have the energy generated by heat source. So, if it is V into I, in that case the energy transferred to workpiece Q may be taken as equal to eta V I. So, that is what we mean to say, that Q can be found by eta times V into I. So, V, if you use the electricity as the source of energy, in that case V into I multiplied by eta, that may be giving you, that is voltage and current which is used. So, that may tell you that is typically in the case of electroslag or electron beam welding cases. So, where you use that electricity. So, in that case voltage and welding current, if you have V and I, so eta may be used as Q may be used equal to eta into V into I. Now, the thing is that this efficiency of the welding processes vary. Different welding processes have different efficiencies. Now, let us take the example of consumable electrodes like SMAW, SAW or GMAW, like shielded metal arc welding, submerged arc welding, gas metal arc welding. Now, in these cases what happens that you use either of the polarity. Now, in that case ultimately the heat goes to the workpiece. So, the efficiency is quite higher. Now, if you talk about the gas tungsten arc welding, now in the case of gas tungsten arc welding, it is seen that if you use the DC current and if you use this DCEN, electronegative and work positive, in that case more heat is because of the electron bombardment is at the workpiece. So, you will have more heat generated at the workpiece. So, that gives you a better efficiency, whereas if you use the gas tungsten arc welding with AC, in that case you have half of the cycle only effective. So, ultimately you will have arc efficiency lower as compared to DC case, DCEN case in the case of gas tungsten arc welding. Now, coming to suppose the electroslag welding. Now, in the case of electroslag welding, what happens that it is lesser than SAW. Now, if you look at the these consumable electrodes welding, in that the SAW is even better as compared to others, because in SAW case, as we know, in the submerged arc welding, the arc is under the blanket of flux. So, the dissipation of heat from that arc to the surroundings is lesser. So, in that case, the arc efficiency or thermal efficiency of this process is better as compared to other processes. Now, when we compare it with electroslag welding, then it is better, but then it is not as good as SAW because of the water cooled copper shoes in these cases used. So, that way it has some adverse effect on the thermal efficiency or the efficiency of the process. Or then if you talk about the electron beam welding, now electron beam welding, this has a very high thermal efficiency, and this efficiency is normally of the order of close to 100 it may go. It is because of the keyholing phenomena, because it makes the hole and that works as a black body type of property. So, that basically does not allow the heat to dissipate, and so this welding is very effective in the case of these electron beam welding and all. So, they here they are trapping most of the energies, and that is why the efficiency is quite high. Now, if you take the example of laser welding, now this laser welding, here the efficiency will depend on the wavelength and energy density of laser beam. So, that is workpiece material, laser beam, surface condition and joint design. So, many a times what happens that if you take very polished surfaces like aluminum or copper, in that case the reflectivity is quite high, and then you have very low efficiency. It also depends upon the type of laser beam, what is the density, power density and all that. So, that way it can have very small value of efficiency also. So, then in the case of oxyacetylene welding, you have the other parameters like nozzle diameter, then you have welding speed, then material thickness, all this conductivity. These are the important parameters which decide about the efficiency. So, in a nutshell, if you try to see the efficiency, the GTAW varies from 50 to 80 for DCEN, and it varies from 20 to 50 for normal AC. Similarly, submerged arc welding will be about 65 to 85 percentage. Then you have submerged arc welding, if you look at it, goes from 80 to 99%, quite higher among the arc welding processes. Then electroslag welding, if you see, it will be 55 to 82% is reported. Then electron beam welding will be close to from 80 to 95% of efficiency is reported. And then you have laser beam welding, it will be about, it starts from 1 to even 70% of that efficiency is seen. Oxyacetylene welding is from 25 to 80%. So, now again depending upon the different parameters. So, this way these efficiencies of the heat sources vary. So, this is in a nutshell about the heat thermal aspects in the welding, and typically the heat flow and about the efficiency of heat sources, then about the isotherms and all that. We will discuss about other aspects in our next lecture. Thank you very much.